Anyway, I think if you're staying where you are, then you're.
Okay, yeah. I'll seems that it's working.
Okay, yes.
Okay,
Yes.
okay, great. Yeah, so then I guess I can continue from where I was. Yeah, so as I was saying, this work is an introduction to the UPMEM programming model and the PIM architecture, micro benchmark-based characterization of the DPU, and a benchmarking and workload suitability study. So our main contributions are the comprehensive characterization and analysis of this architecture, and a benchmark suite that is called PRIM benchmarks, 16 workloads, as you'll see, that are memory bound in conventional processor-centric systems. We have characterized these workloads with strong and weak scaling experiments and compared to their CPU and GPU counterparts. Takeaways of our work are workload characteristics for PIM suitability, programming recommendations, suggestions, and hints for hardware and architecture designers, and the PRIM benchmark suite that can serve as programming samples and for evaluation and comparison of current and future PIM systems. For a little bit of motivation, again, data movement in current computing systems dominates performance and energy consumption. These are just some motivational numbers. 62% of the total energy is consumed on data movement in consumer applications, 40% in scientific applications, 35% in mobile applications. And the reason for that is that there is a lot of data movement among all these components in the compute system, a system on a chip, for example, with CPU, GPU, accelerators, cache memories, and the external DRAM. There's a lot of data movement, and we believe that compute systems should be more data-centric, and that essentially means computing where it makes sense. And that's what processing in memory can provide, computing where the data resides. This is one slide from Professor Mutlu, where you can already see a picture of the UPMEM DIMMs. These are conventional DDR4 DIMMs. There are typically, well, here it says 16, but we have also played with a version with 8 chips per DIMM. Essentially, inside each chip, we have 8 memory banks, and near each memory bank, there is a small processor, an in-order processor, as you'll see, that is called DRAM Processing Unit, or DPU. To give you like the very, let's say, like the final takeaway of this work from the beginning, because many times we received the question why this is better than a GPU, for example, or other accelerators. I want to say that it's definitely not something that needs to substitute other conventional systems. I believe that processing in memory is a paradigm that can supplement processor-centric systems with CPUs and with GPUs. But what we have observed is that these UPMEM-based PIM systems can outperform state-of-the-art CPUs in terms of performance and energy efficiency for most of the workloads that we have tested. And they can outperform GPUs, the state-of-the-art GPUs, for a majority of these workloads, in particular for 10 out of 16 of the workloads or benchmarks that we have tested. And they also prove to be more energy efficient for those workloads where they also perform better as well. You can find all the details of our work in the short version of the paper that we first published in 2021, then a longer version in 2022. And in this presentation and also in the papers, you will find these color boxes with programming recommendations, observations, and key takeaways. So let's start with an introduction to and an overview of the UPMEM-based PIM system. It follows what we call the accelerator model. The UPMEM DIMMs are integrated into the system and coexist with conventional DDR4 DIMMs. They follow, or we follow here, what is called the accelerator model. The UPMEM DIMMs can be seen as a loosely coupled accelerator. So we have to explicitly move data from the main memory to the PIM-enabled memory, and also have to explicitly launch the computation onto the UPMEM processors. This in some way resembles GPU computing with discrete GPUs. If you take a look at the system organization, as I said, the UPMEM DIMMs coexist with DDR4 DIMMs. As you can see in the picture, these DDR4 or other memory technology, but in the end, we have a main memory, a standard main memory, and then we have the PIM-enabled memory. We can take a closer look at the PIM-enabled memory or the DIMMs. As I said earlier, there are typically 8 or 16 chips, and inside each chip, there are 8 DRAM banks that are called main RAM or MRAM, and next to each of the banks, there is one DPU or DRAM processing unit. This is one of the systems that we have used in our evaluation, is the larger one. As you see, it's a dual socket CPU. In total, the PIM-enabled memory contains up to 2,560 DPUs and 160 gigabytes of DRAM. And this is a picture of the system with the 2 CPUs. Here you can identify the DRAM DIMMs, and these are the UPMEM DIMMs, the PIM-enabled memory. And this is a view of the smaller system. That was the first one we could access with only 640 DPUs and 40 gigabytes of DRAM. Feel free to interrupt me and ask any questions over the course of the presentation. Okay, let's start with very briefly introducing how we typically partition the workload across the DPUs or the DRAM processing units. Vector addition can be your first programming example. In vector addition, same as we can do in other parallel processors, what we do is dividing the input and the output in equally sized chunks. They are assigned to different DPUs, and then inside the DPUs, because they are multi-threaded processors, we have PIM threads running. These PIM threads are called tasklets. So inside each of the DPUs, we would have each tasklet operating on part of the chunk that was assigned to the corresponding DPU. So this is for DPU 0, 1, 2, and 3. It's important to understand in this system how well or how bad perform the data transfers between the main memory and the PIM-enabled memory. We call them CPU to DPU or DPU to CPU transfers. It's important because obviously the execution always starts in the host. So the first thing that you have to do when running your program is moving the data from the main memory to the PIM-enabled memory. And there are different ways of doing that. There are actually 3 ways that the SDK provides. First one are the serial CPU, DPU, or DPU, CPU transfers, where we transfer a single buffer to a single MRAM, a single DPU. Then we also have parallel CPU, DPU, and DPU, CPU transfers. In this case, we target multiple DPUs, and we are going to transfer one buffer or one part of a buffer to one of the different DPUs. And finally, we have broadcast CPU, DPU transfers, where we transfer the same buffer to all DPUs and to all MRAM banks, or those that we have allocated. You obviously don't need to use all the DPUs in your system. As I said, it's important to understand how these CPU, DPU, and DPU, CPU transfers perform, because there is no direct communication channel between DPUs, at least in the current generation. So all inter-DPU communication takes place via the host CPU. And there are different possible example communication patterns. For example, in our work, we have experimented with simply merging partial results to obtain the final result. This only requires to move the partial results from the DPUs to the CPU and then perform merging on the host side. Or in typically iterative algorithms like graph processing will have to redistribute intermediate results for further computation. This is a little bit more complex and obviously higher overhead, because here we need DPU, CPU, and then CPU, DPU transfers. We did some micro-benchmarking to measure the sustained bandwidth for these different types of transfers. In particular, I'm going to quickly show you two experiments. In the first one, we target a single DPU, a single MRAM bank, and we change the transfer size from 8 bytes to 32 megabytes. And then in one rank, we transfer 32 megabytes to or from a set of 1 to 64 MRAM banks that are all in the same rank. I'm not sure if I said that earlier, but one rank is 8 chips and in total 64 DPUs. So in each DIMM, we have 2 ranks. So we have typically 128 DPUs. I'm not going to show you results for experiments with more than one rank, but as you can expect, what we observe in our preliminary experiments is that you can exploit channel level parallelism.
Why do you not allow DPU to DPU transfers?
There's no DPU to DPU transfer direct because the company didn't design any way.
Is that a good decision on their part?
I don't think so.
I don't think so either. But it's not your fault. It's the company that's producing it.
Yeah, I'm going to show some results later. You'll see how this impacts many of the workloads. And yeah, we are already thinking about how this could be fixed in future architectures. So yeah, so results for one DPU, data transfer size varies in these experiments between 8 bytes and 32 megabytes. Here in the x-axis, you see the transfer size, as I said, from 8 bytes to 32 megabytes, and here it's a sustained bandwidth, right? Either from CPU to DPU or from DPU to CPU. So these are results from CPU to DPU. These are from DPU to CPU. As we see, the bandwidth increases as we transfer larger chunks. At some point, it starts saturating, but in principle, larger CPU, DPU, and DPU, CPU transfers are better result in higher sustained bandwidth.
I'm just curious what happens after 32 MB. I mean, particularly the top trend.
Yes.
I'm not quite sure if that's going to saturate or if it's coming down.
No, I don't think. I mean, it keeps more or less flat. Keep also into account that maximum that you could transfer is 64 megabytes because that's the size of the MRAM. So that's why I run the experiment up to 32 megabytes. But yeah, that would be like a couple of points later, but yeah, it keeps flat. And here we have results for one rank. Here, the size of the chunk that we are transferring is 32 megabytes. We change the number of DPUs from 1 to 64. And if we use the serial transfers, because we are targeting a single MRAM bank at a time, so we are essentially going to one MRAM bank after other, right? So it's completely serial. So that's why the bandwidth doesn't increase when we increase the number of DPUs. If we use the parallel transfers or the broadcast transfers, we can see that the bandwidth increases more or less linearly. And so, yeah, the sustained bandwidth of parallel CPU, DPU, and DPU, CPU transfers increases with the number of DRAM processing units inside a rank. A couple of more observations that are not in the slide. First of all, you can see that the CPU to DPU transfers, either serial or parallel, are usually higher bandwidth than DPU to CPU. That's due to the way that they have implemented, the runtime library implements the transfers. As far as I know, they are using AVX instructions. So for the CPU to DPU transfers, they are using asynchronous writes, and that's why they achieve a little bit more bandwidth. The case of the broadcast transfers is especially good because it's transferring a single buffer to all DPUs up to 64 in this case. So yeah, it essentially has better locality in the CPU cache. So that's why we see that higher bandwidth in that case.
Because this is a measurement study, I was wondering how do you statistically make the sample?
How many runs?
Yeah, how many runs per each? That's first question. And second, I was wondering, and that might be a nice question, what happens to latency? We're talking about bandwidth here.
Well, latency. First question is that I don't remember exactly, but yeah, we average many runs here, like at least 20 or something. So after warming up as well. So I repeated experiments many times. I have to say that you may also see some change from a system to another system. In the end, I thought it was really important and necessary to measure this to kind of have an idea of what was the bandwidth here, but it's not something fundamental to this system, I would say. Then in terms of latency, I mean, in the end, I had to measure the latency, right, to obtain the bandwidth. But why? So what's the point? What's your point?
Bandwidth, throughput and latency kind of at the odds with each other, right? You can have better bandwidth. So I'm drawing experience from another context. That's why I said it might be a question.
Yeah, well, I don't have any specific observations about latency. What I can tell you is that in the end, maximum bandwidth, or the best you can do with this, is the best you can do with the memory bus. And indeed, it's a very good question and very good discussion, because here is where the actual data movement bottleneck gets exposed, right? We have to move the data from the main memory to the PIM-enabled memory, and the system, or the overall performance, is suffering there. But that's in the end because it's falling in the classical problem, right, of the data movement. In the end, if you want to obtain maximum possible bandwidth here, you need to target the whole rank. That's why we see up to 16 gigabytes per second for 64 DPUs. I think that the theoretical maximum of DDR4 is 19. So we are pretty close. But yeah, if you target a single DPU, is just a single chip, so for sure not exploiting even what the memory channel can give you, right?
But it's far less than an eighth of the memory channel.
It's which one?
For one, you would expect to have roughly an eighth of the overall channel bandwidth if there are no additional sort of routers or latencies that are blocking you.
Yeah, I don't really know the inner details of that, and yeah, and these experiments, I can even tell you that they were a little bit problematic. The results that I'm showing here correspond to the larger system, but interestingly, we achieved a slightly higher bandwidth as well in the smaller system. It's something that I even tried to check. I mean, I checked and tried to understand with UPMEM folks, and yeah, they can keep continuously improving their driver, and maybe if we repeat these experiments now, it will be even better. So, but yeah, as I said, we included these results in the work for completeness, but I don't even think that, well, I mean, in some sense, we should take them with a pinch of salt, because it's not something inherent or fundamental to the UPMEM system itself.
Eric mentioned this, but what is relative to the main memory size? how much is being enabled memory? Is it like half, 25%, 10%? How much is being enabled?
The main memory. If I recall correctly, that main memory is 64 gigabytes. The total that they have in the dual socket system. PIM enabled memory is 160 gigabytes. So why did they configure it this way? I guess it's because they try to maximize the number of DPUs that they have in the system. So the system can support up to 20 DIMMs, that's 40 ranks, and 2,500 DPUs.
And then initially, when you bring stuff, you know what you are going to actually with the PIM, put that in the neighborhood, so you can avoid some of the time. If you know what you are doing, that's really with the PIM.
Yeah, but the thing is that if you want to access the PIM enabled memory, you have to perform one of these transfers. So, I mean, in the end, processing in memory makes a lot of sense for data that doesn't need to move, right? For example, if we are training a machine learning algorithm, we can have the training data set distributed over all DPUs and keep it there and then repeat as many iterations as we need. So in some sense, we can consider that this overhead will be amortized. Yeah.
Just to clarify, the PIM enabled memory doesn't show up in the normal address space. You require special access to it.
Yes, I think so. So it's
OS cannot run out of it or anything else.
No. It's not in the virtual memory space. But yeah, it's I mean, yeah, this is like a tricky discussion, right? Because ideally, it would need to be the main memory.
So is there, on the PIM enabled chips, is there no mode bit or something that you can say, I'm gonna turn this off and obviously it's just like here. And so in the beginning, then I load that and then turn the mode again, anything like that?
I would say, I mean, the interface is a DDR4 interface. So I believe that if you want to use those chips as regular memory, you could, but probably you could not do anything with the DPUs, right? You would be only accessing them as regular DRAM.
You know, the OS not done from it, like you said, so like, I'm maybe trying to trick the OS into saying, in the beginning, we have this mode fix setting that I just turn off, and now this behaves just like normal DRAM, so the OS can do whatever it wants from this memory, normal analogs or whatever. And then at some time you say, I'm not confused, so turn that bit off. Just saying, I mean, of course, it's a hardware decision that they probably took, you know, when they decided. So maybe there are some hardware constraints and limitations that does not allow for that.
I guess there must be. If I tell you the truth, I even asked them directly why this is not main memory. I never got a very clear answer, if I tell you the truth. And yeah, I myself don't have a good answer to this.
Maybe the clear answer is that the memory is like what we call a scratch pad memory, which is not known to the operating system. It's there as part of the DPU for the purpose of processing at the DPU. So you need to transfer data to the DPU, process it, and then transfer it wherever it's going to be needed next. The operating system doesn't have to get involved. You can have that be done by instruction. My earlier question about DPU to DPU would be in hand. So I think this transfer, I like to think into it, rather than have the CPU be a bottleneck and transfer because we don't only want to. What I'd rather do is think like DMA. So the CPU may initiate it, but then the transfer goes, and it could go from a DPU where processing has already been done to a DPU where processing needs to get started. In fact, there is some history of doing that in the literature. They call it marshaling, I guess, the data before you start processing. But it doesn't, the concept of thinking of it as scratch pad memory for that DPU. In fact, I would argue that that you have an accelerator that consists of the DPU and the memory that's associated with that, and the scratch pad memory that's associated with it, which is much more than a register set. Anyway, I've talked more than.
Okay, yeah, thank you very much for the comments.
The performance of parallel and broadcasting. So why do we have like 10 gigabytes per second higher like speed?
Yeah. Yeah, it's I also see a lot of difference there. We didn't really do so. Take into account as well that here we are. I mean, we don't own the server. We are accessing a server that we got access to from them from UPMEM. So we could not profile in detail or so. Let's say the intuitive explanation is that when you are using broadcast transfers, it's a single buffer that in this experiment is like 32 megabytes, and this single buffer is transferred to all DPUs. So it's likely that it's in the cache and the L3 cache when we are targeting all the different DPUs, and that's why we are saving the time from bringing from the main memory to the cache, and then from the cache to the PIM-enabled memory.
So you are only sending 32 megabytes, not more than that?
Yes. It's only 32 megabytes, as I said earlier, is because the size of the MRAM, that is the memory, the DRAM of each of the DPUs, is 64 megabytes. So it doesn't make sense. Well, you could have larger, let's say 40 megabytes or 60 megabytes or something like that. Could be done as well, but in the end, it's a single buffer to all DPUs.
If you're sending the same 32 gigabytes,
No, megabytes.
32 megabytes. Parallel, so you mean 32 megabytes per DPU, like DPU? Is that per site for each DPU or for entire DPU?
It's for each DPU. A single buffer. Okay. Okay, well, we can continue the discussion on this later if you want. Okay, now let's take a look at the DRAM processing unit, that's the micro benchmarking we did here. I don't know if there are any questions in the chat.
I'm monitoring.
Okay, thank you. Okay, so yeah, for the DRAM processing unit, we run different experiments in order to measure the arithmetic throughput and also the bandwidth to these two memories, the WRAM and the MRAM. And this is the PIM system, as you remember, the PIM chip. In more detail, we can see DDR4 interface for the host to access the MRAM banks, the control and status interface. Here we have the MRAM banks. In total, there are 8 64 megabyte MRAM banks in each of the chips, and each of the DPUs access the MRAM bank using this DMA engine that can move instructions from the MRAM bank to the instruction RAM, or operands data from the MRAM bank to the scratchpad, to the WRAM. As you see, 64 kilobytes in size. And then we have the pipeline. We take a closer look at the pipeline. There are in total 14 pipeline stages. It's running up to 425 megahertz in the latest DIMMs that they have. In the ones that we use in this work, they run at 350 megahertz. And it's a fine-grained multi-threaded in-order processor with 24 hardware threads. So the micro benchmarking, first thing that we did here is measuring what's the maximum arithmetic throughput for different data types and operations. Operations are addition, subtraction, multiplication, and division, and data types, integer, 32-bit and 64-bit, floating point, and double. And in these experiments, we are not purely measuring the throughput of the pipeline itself, but also including the access to the WRAM, because there is where the operands reside. And if you check the assembly code, you'll see that essentially every single operation needs to first go to WRAM, bring it to the registers, then compute, and then write back to the WRAM. So that's why we included those accesses in the analysis. And here you see the results for different number of tasklets from 1 to 24 in the x-axis. The y-axis is the arithmetic throughput in mega operations per second. These are the results for addition and subtraction of 32-bit integers, and these are for multiplication and division, and these are for the rest of the data types. So a key observation is that the arithmetic throughput always saturates at 11 or more tasklets. And this is consistent across data types and operations, and relates to the number of stages in the pipeline. Recall that there are 14 stages. Let's say that the last 3 stages can be overlapped with the next instruction for each of the threads. Another observation is that the throughput is significantly higher for the addition and subtraction compared to the 32, I mean, the integer multiplication and division, and also the floating point operations. And this is because the pipeline or the ALUs only support native addition and subtraction of integers, while the other operations are emulated by the runtime library. In the case of the 32-bit multiplication, for example, they use a shift and add implementation, and it might take up to 32 cycles for 32-bit integers. In the paper, we also have some analysis of the access to the WRAM. I don't have anything here. I mean, I have some backup slides if you want to check them. But yeah, the summary is that one access to WRAM is essentially the same in terms of throughput as one addition or one subtraction. So you can perform, when the pipeline is full, you can perform one access per cycle, 8 bytes per cycle, typically. And we have also analyzed latency and bandwidth of this MRAM. Yeah, what's the latency and bandwidth when moving data between the MRAM and the WRAM. We did this for different access patterns, as you're going to see. First thing was measuring the latency of a single DMA transfer. There are 2 types of transfers, obviously. MRAM read are copy from MRAM to WRAM, and MRAM write from WRAM to MRAM. And then I'm going to show you as well results for the stream benchmark, and then for strided access pattern, and for the random access pattern. So let's start with the latency. So we did the analysis for different data transfer size between MRAM and WRAM, for MRAM read and for MRAM write. We measured latency and then calculated the bandwidth. So as you can see, the latency can be modeled with a simple linear expression, and the model fits pretty well. In these measurements, beta is equal to 0.5 cycles per byte. So this results in a theoretical maximum MRAM bandwidth of 700 megabytes per second for a single DPU. So in total, for the whole system with 2,500 DPUs is about 2 terabytes per second. And so yeah, key observation here is that the latency increases linearly and that the MRAM bandwidth is 2 bytes per cycle. Then some results for the stream benchmark. Here we have 2 versions of the stream benchmark. The first one is, well, I mean, copy and copy DMA. So we have, let's say, the 4 stream benchmarks, but for copy, we have copy and copy DMA. The difference is that copy DMA is simply using an MRAM read to bring one chunk of typically 1 kilobyte or 2 kilobytes to the WRAM and then write it back. So that's the copy DMA thing. And the other one, copy, brings the chunk to the WRAM, and then we go one by one over all the elements of this chunk, and then we write back. For addition, scale, and triad, we use a similar approach to the copy version. And these are the results. Here we increase the number of tasklets from 1 to 16, and we measure the sustained MRAM bandwidth. First, you see the results for copy DMA. Here, the DMA can only sustain a single transfer at a time. It's only that you see a slight increase in the overall bandwidth when you use 2 or more tasklets, but that's because if you use 2 or more tasklets, there is always one transfer ready to get issued as soon as the previous one finished. These are the results for copy and add, and the saturation points happening at 4 and 6 tasklets. And then these are for scale and triad with the saturation at 11 tasklets. So there are 2 key observations here. In some cases, or in the case of copy DMA and add, we see that the performance or the bandwidth in this case saturates with a number of tasklets that is smaller than 11. And this happens because the latency of the MRAM to WRAM transfers is larger than the pipeline latency. There is very little computation in these 3 micro benchmarks. So that's a memory-bound workload in this architecture. And in the other 2 cases, scale and triad is the pipeline latency that is hiding the MRAM latency. So that's why we see the saturation point at 11 tasklets. And that's a compute-bound workload. And as you can expect, that's going to be the normal case in this architecture. Okay, there is a flag here. There are also some results for strided access pattern. Here we follow 2 possible approaches. In the first one, we are bringing, it's what we call coarse grain. We bring one whole chunk of continuous data to the WRAM and then perform the strided accesses in WRAM. The fine grain approach is just bringing the 8 bytes you need to access. So as you can expect, for the fine grain strided accesses, the overall bandwidth or the effective bandwidth is in principle going to be lower, right? And then for the random access pattern, we follow the fine grain approach. So here you see the results for the x-axis is different strides, y-axis is the MRAM bandwidth, some results as well for different number of tasklets. Maximum you can get for stride 1 is, as we could expect, very similar to what we measure with the stream benchmark. And then the effective bandwidth of the coarse grain approach goes down because we are not accessing the whole chunk that we bring to memory, right? We are accessing in a strided manner. So in principle, the bandwidth of the coarse grain accesses is significantly larger than for the fine grain accesses, and for the random accesses is very similar. Random are here, only this column here, as you see, very similar to the fine grain strided. So the interesting observation here is that the coarse grain approach makes sense up to a certain point, up to a stride of 16, or for a stride of 16 or larger, then it makes more sense to start using the fine grain approach, because otherwise we would be bringing a lot of data that is not really used in the WRAM. So one programming recommendation is to use the coarse grain approach when the stride is going to be smaller than 16, and use the fine grain approach for larger strides or random accesses. Then, another set of experiments was to measure the arithmetic throughput versus the operational intensity. So goal is to do sort of a roofline model here. We bring one whole chunk of data, 1 kilobyte, to the WRAM, and then on each of the elements in this 1 kilobyte of data, we perform a variable number of operations. We change the operational intensity. Operational intensity here defined as the number of arithmetic operations performed per byte accessed from MRAM. And here you can see some results for operational intensity from a very, very low value to something relatively high, 8 operations per byte. Each of these dots corresponds to the number of tasklets that we have used in the analysis. And here, the y-axis is the arithmetic throughput. So you can see clearly that there are two regions, memory bound region and compute bound region. In the memory bound region, the performance, as we could expect from the previous experiments, performance saturates at the number of tasklets that is lower than 11. For example, here is like 2, at some points 3, and then at some point it will saturate at 11 tasklets. When it saturates at 11 tasklets, then the performance is, or the throughput is flat at its maximum, and yeah, then we are in the compute bound region. And this throughput saturation point is very, very low, even for addition of 32-bit integers. As you can see in the slide, is 1/4 operation per byte. And it's even worse for more complex operations and data types. So in most cases, we will find that, well, the arithmetic throughput saturates at a very low operational intensity. So we can say that the DPU is fundamentally a compute-bound processor, and we can expect that most workloads, real-world workloads, will be compute-bound on this architecture. Any question here?
You're assuming that the access pattern is preferential here for this conclusion, right? If I had an access pattern that I was not using my buffer well, I would be at a much.
Yeah, that's a very good point. and that's actually something that we didn't analyze in this paper because here we just assume streaming accesses, bringing one large chunk to the WRAM. And this way we can exploit the maximum bandwidth, but something that we have observed in workloads with more irregular accesses where we need to use these fine-grained accesses is that in those cases, those fine-grained accesses become the bottleneck. That's a very good point.
You bring in a kilobyte in a coarse-grained access.
Yes.
How much of that doesn't get used at all?
In these experiments, yeah, the whole thing.
The whole thing gets used.
Yes.
Everything gets used.
Yes. Okay. Any other question? Okay. Well, so now we are done with the analysis of the DRAM processing unit. As I said, there are more details in the paper, and also have a few more slides as backup, and also with more details about the micro benchmarks themselves, if you are interested. But now let's talk about the benchmarks themselves. So we call them PRIM benchmarks, processing in memory. As you can imagine, it's a common set of workloads that can be used to evaluate this PIM architecture, compare software improvements and compilers, and compare future PIM architectures and hardware. Two selection criteria: first of all, workloads from different domains, and workloads that are memory bound in processor-centric architectures. In total, there are 16 different benchmarks for 14 workloads, because we have a couple of different versions of 2 of them. And these are the application domains, are relatively simple codes, but more or less, let's say, complete set of different patterns. From dense and sparse linear algebra, databases, graph processing, neural networks, etc. So we use the roofline model just to make sure that we confirm that they are memory bound on a CPU, in order to have a nice plot in the paper. And in terms of diversity, they are also diverse in terms of memory access patterns, operations and data types, and communication and synchronization needs. As you can see, we distinguish between intra-DPU and inter-DPU. For intra-DPU, we can use the synchronization primitives that the SDK provides, in particular barriers, handshakes, mutexes, and semaphores. And some of them require as well inter-DPU communication in different ways. In some cases, for example, a histogram calculation is just generating subhistograms and then bring them to the host and then merging the subhistograms in the host. In others, it's more complex, like for example, in BFS, we we have to bring the partial frontiers to the host, merge them, and then redistribute the workload or the computation over the DPUs. We have evaluated them, strong and weak scaling experiments on both PIM systems. I'm going to show you results, some strong and weak scaling experiments on the larger system for one DPU with different number of tasklets. In one rank, we have strong and weak scaling experiments and up to 32 ranks, that is up to 2048 DPUs. And then the comparison to the CPU and the GPU, an Intel Xeon and NVIDIA Titan 5. So here you see the results for the 16 DPUs, for the 16 benchmarks on one DPU. We changed the number of tasklets from 1 to 16 and show the breakdown of the execution time. This is the execution time, so it's a DPU time, the execution time of the kernel itself on the DPU, the inter-DPU communication where you need it. This is not the case of this benchmark. Then the CPU to DPU time and the DPU to CPU time, and also the plot includes the speed up over one tasklet. So in general, observation is that we see how the execution time in this type of workloads that are relatively simple and can exploit the bandwidth. The general observation is that we see that when increasing the number or doubling the number of tasklets, we see that the execution time reduces by half up to 11, and then the performance saturates. And that's actually the first observation, is that in these experiments, the best performing number of tasklets is 16, because we used 8 and 16. But as I said, we see more or less, you can see it here, almost 2x speed up when we double the number of tasklets up to 8, and then a little bit less from 8 to 16.
I'm curious about a couple of things, but one is the speed up is for the part that's on the DPU only.
Yes,
Like, some of them
true, yeah.
These transfer times that are dominating. So
Yeah. So, and in this case, the transfer time is constant as well here, because it's
excluded from the speed up.
It's excluded from the speed up, yes.
So the actual speed up is much less than
The actual speed up would be much less, yes.
and
You can see here, for example.
and the inter DPU is basically to the host and back.
Yes, there is no inter DPU in this particular set of experiments because it's a single DPU. But you can, you're going to see it in the next result. Well, the first observation is that number of tasklets more than 11 is typically a good choice for the number of tasklets. Some of the workloads don't use intra-DPU synchronization. In other workloads, there is intra-DPU synchronization, but it's quite lightweight. And these three workloads, BFS, one of the versions of the histogram calculation, and one of the steps of the transposition use mutexes. So they really hurt the performance. And it may happen, for example, in this one, that the best performing number of tasklets is not 16. In this case, is only 8. And these are experiments on one rank. I don't have many slides for this to not make it too long. But yeah, you can see here this darker thing is the inter DPU overhead, right? And actually, in some cases, it's pretty high. For example, for BFS, it almost doesn't make sense to use 64 DPUs due to this overhead. And that's even more noticeable if you go to up to 32 ranks. Notice how some of the workloads like BFS or NW or MLP, they have very, very high inter-DPU overhead or inter-DPU communication time. So yeah, I mean, the BFS is pretty bad indeed. Yes. Always.
And the barriers and stuff. benchmarks, they're all like, intra DPU, right? There is no.
Yes, they are intra-DPU. By the way, the implementation of these barriers is also not very efficient. We have some measurements in the appendix of the paper as well. And yeah, one of these barriers might take up to 1,000 cycles or so. It's something where some hardware optimization is possible for sure. They eventually mentioned that they could have more efficient hardware-based barriers at some point, but I don't know if that will happen in the next generation. Okay. Yeah, well, the presentation could be very, very long, so that's why I don't have so many details. You see, this is key observations 17 and 18. If you want to, read all of them in detail, you can go to the paper, but we also have weak scaling experiments. As you see in weak scaling, so one general observation is that the DPU time remains flat when we increase the number of DPUs. The bandwidth doesn't scale linearly. It's something that we observe in the micro benchmark experiments of the CPU, DPU, and DPU, CPU bandwidth, right? So that's why we see this increase in the communication time, but yeah, also it's not a linear increase. It doesn't remain flat, but yeah, it's because it's sublinear.
I'll ask you later.
Okay, you have a question?
Yeah, just like maybe tedious question, but like would the NW wide, just like increase the DPU time to the NW?
Yeah, that's a very good question. We actually have a section to explain that in the appendix. It's because the algorithm itself. So NW, essentially you go anti-diagonal by anti-diagonal, generating this two-dimensional matrix, right, for the dynamic programming algorithm. The fact that you increase the number of DPUs doesn't mean that you are exploiting more parallelism in the smallest diagonals. In the end, you can imagine the two-dimensional matrix is divided into tiles, and these tiles form the different anti-diagonals. So in the very first iteration, it's just one tile, so it's just one DPU, regardless of how many DPUs you are going to use later. So in the appendix, actually, you will see that we analyze as well. We run the same experiment, but only measuring for the central anti-diagonal, that is the larger one. And in that case, we see that is completely flat. But yeah, that's a very good question. Okay. Okay, now let's take a look at the comparison to the CPU and the GPU. As I said, comparison with an Intel Xeon processor, desktop processor, and an NVIDIA Titan V. One thing that I would like to highlight up front is that we use the largest data set that can fit in the GPU memory. I don't remember this one. I think it's 12 gigabytes, the size of this, the memory of this Titan V. A100 has, I think, has a version with 80 gigabytes, and the H100 will also have 80 gigabytes, as far as I remember. In the larger system, the larger UPMEM system, there are up to 160 gigabytes. We are not taking advantage of that, right? That's why we use a data set that fits in the GPU memory. And we are including in the overall execution time, including DPU kernel and inter-DPU communication, which means, if I'm not wrong now, that we didn't include the data transfer, the initial data transfer and final data transfer, neither in the GPU or the UPMEM system. But for the UPMEM system, we are including the inter-DPU communication, okay? So we tried the comparison to be fair. And these are the results, speed up normalized to the CPU execution. These are, we differentiate between more pin suitable and less pin suitable. We can go to a little bit of analysis here. But first of all, comparison to the CPU, both systems outperform the CPU, both systems outperform the CPU for 13 of the 16 benchmarks. These three, SPMB, BFS, and NW, are greatly burdened by the inter-DPU communication, or in the case of SPMB, is because it's a version that uses floating point. So its operations are emulated, but for the rest of the remaining 13 PRIM benchmarks is significant speed up, as you can see, 93 or 27.9, even for the smaller system. And then we have the comparison to the GPU. We observe that the larger system outperforms the GPU for 10 of the PRIM benchmarks with an average of 2.54 times. The smaller one is slower, but still within 65% the performance of the GPU for these PRIM benchmarks.
I was just wondering, do you have insight into
Why these are faster?
some of these workloads, right?
So actually, the 10 more pin-suitable workloads have three characteristics. The first one is that they use streaming memory accesses because it's the way of achieving the maximum bandwidth in the UPMEM system. There is no or little inter-DPU synchronization. In some of them, there is inter-DPU synchronization. For example, in this is histogram, and these are the two versions of scan. There is some inter-DPU synchronization there, but it's not so significant compared to the overall execution time. And the third point is that they don't use or have little use of integer multiplication, integer division, or floating point operations. And so these three characteristics make a workload potentially suitable for the UPMEM PIM architecture.
Is there a way to like normalize these? Like, I just want to get a feeling of, okay, the 640 DPU, is that compared to, 100 SMs on the GPU, or is there another way to normalize that cost? Do you know how much expensive it is to buy, or maybe power?
Yeah, we didn't do that, but UPMEM folks themselves have one paper that they they published in some bioinformatics conference. Is about variant calling, and there they reported total cost of ownership, including what's the cost, what's the energy consumption, etc. And yeah, I mean, it's their paper, right? So if you read their paper, then the system is amazing. But yeah, I think that's it's a good metric. It's something that we somehow discuss in the paper. We have a short section where we discuss about that. But yeah, I mean, it's also, if you ask about the price of the DIMMs, I don't know exactly the price, but it might be around 100 euros each DIMM or something. So if you have 20 DIMMs, then it's not much cheaper than a powerful GPU, right? I mean, powerful GPUs are probably more than 3,000. But yeah, in the end, I guess it's also, I mean, it's a very small company, right? So they cannot have very large mass production and this way reduce the prices. But yeah, I think that this kind of analysis is also pretty interesting. But it's also not fair, right? Because it's not the same to fabricate a few DIMMs or fabricate thousands of GPUs every year. But yeah, those are very good considerations for the comparison.
So just now, you are using like 25 to 56 GPUs, right? So
Yes.
like one DIMM has 64 GPUs or 64 banks, because like we have 8 chips and then 8 banks.
What happens with those 4 that we are missing?
Yeah.
They were faulty.
Okay, so you are just like disabling that when you...
Yeah. I mean, I don't I don't know if this is even something that they do themselves when they detect that something is faulty, or the driver checks. I mean, there is a command for the driver to check what's the status of the DPUs. And we sometimes detect that something is going wrong, and then, yeah, run this command, and it says, oh, there are some number of faulty DPUs. We tell them, and they said, oh, we are going to reboot the system. I don't know those details, but yeah, some of the DPUs were faulty in this analysis. I can continue. Okay. Yeah, I'm going to. Well, I still have a few slides, but anyway, this is energy comparison. We could only run energy experiments on the smaller system. It wasn't possible to measure energy in the larger system. But yeah, anyway, the key observation here is that wherever you can get performance improvement, you can also get energy savings compared to the CPUs and the GPUs. And key takeaways, first of all, they are, as you have seen, fundamentally compute bound. The throughput saturation point is pretty low in all cases. Second key takeaway is that the best workloads are those that don't use arithmetic operations or not many or simpler operations, and not floating point, not multiplication or division. Third key takeaway, for more suitable workloads to, I mean, those that don't require inter-DPU communication or not so much compared to the overall execution time. And this is the first block that you saw in the beginning with, let's say that the comparison to CPU, to GPU, and also in terms of energy efficiency. I think I can also skip this executive summary again, because I want to very briefly introduce, let's say, follow-up works. By the way, all the code, the scripts, everything is available in our GitHub. I have delivered many times this talk, as you can imagine, and they are all in YouTube and in Professor Mutlu's channel. But we continue working with this architecture. This is an analysis of SPMB that we presented this year at Sigmetrics. We tested different load balance mechanisms, partitioning, 1D partitioning, 2D partitioning, different synchronization approaches. In total, 25 different implementations of SPMB for the different partitioning, synchronization strategies, different matrix formats, and comparison to CPU and GPU. The code is also publicly available, and this is the paper. And more recently, we have worked on some machine learning training workloads, in particular, as of now, linear regression, logistic regression, decision tree, and k-means clustering. I don't have results, so don't worry. Just a few key observations and insights that are kind of predictable for now that you understood the architecture very well. For example, fixed point data representation is beneficial because they are integers. Quantization, because you can probably use 8-bit multiplier instead of using the 32-bit multiplication. Hybrid precision implementations, the use of lookup tables because the hardware doesn't support exponentiation. So we used lookup tables for sigmoid, and then the accesses should be in streaming, and also scaling experiments that we have in the paper. This is available in archive. It's not published work yet, but you can take a look if you want, and if you have any feedback, for sure will be very useful to improve future submissions. And another thing that is currently under review is this framework for high throughput sequence alignment. Here we implemented different sequence alignment algorithms, Needleman-Bunch, Smith-Waterman, GenAsem, that is an algorithm from our group, and WFA, the wavefront algorithm, that is a state-of-the-art in sequence alignment from people from BSc. You may know Mikel and his team. And we presented some of these works in a special session on processing in memory that we organized last summer, and also talk about them in one of the courses that we teach. All materials are online, YouTube videos. We talk about our works and also works from other groups and from industry. Like, for example, there are some lectures about SK Hynix or Samsung recent proposals. And these are just other courses about GPU programming, SSDs, memory, bioinformatics, etc. So that's all for now. Thank you very much for your attention. If you guys have any other questions, I'll be glad to continue the discussion. Thank you.
I think now it's a good time since we're 2 minutes over. Anybody who wishes to leave can do so without insulting anyone. But I think on Juan's schedule, there are still a few minutes. So if anybody wishes to stay and ask a little more, please do. And there is one question from the chat as well. So let's give it a minute. 10 seconds, see if anybody wants to, you know. And Juan, I'll just read out the question from the chat for you. It's a question about why is it an accelerator model? Why separate out the memory from, you know, the UPMEM memory from regular memory? I think there were a couple of similar questions.
Yeah, we had sort of discussion. I don't really have the right answer. I don't know what are the real challenges that they faced to enable this. I guess it's something that is potentially doable. At the moment, one thing that I know for sure, and actually it's even in their patent, is that it's not possible to have concurrent access from the host and from the DPUs. Inside the chip, there is essentially a multiplexer, and it's either access from the host or access from the DPU. So that's for sure one reason why I mean, you could not have, you could probably reserve some of the DIMMs, some of the chips for the main memory, but you could not use at the same time, right?
So I'd like to encourage you not to restrict yourself to this company's product, but rather you're doing research, I think. So if the company does what it does to make money, they have limitations, constraints. You don't have those constraints. And so your job is to look at what they should be doing if they didn't have the constraints. And I'd encourage you to do that, to not limit yourself to just what this company happens to be making available to you.
Yeah, I appreciate that. I work with owners, so you can imagine that we are looking into this, of course, but I'm not going to talk about.
If there's any doubt that you're working with an owner, the last 10 minutes of your talk, just develop that doubt. The other thing I want to, in line with that, the programming model may be able, so my view of the accelerator being the functioning with the scratchpad memory associated with it. If that's what is available, the programming model, if it could take advantage of that, would produce a big performance win, I think. Something to be investigated. You understand what I'm saying?
Yeah, okay. Avoiding the these data transfers.
So so you make data transfers where you need to make the data. And they could be going on in parallel, depending on what the algorithm is going to need.
Yeah, and I also think that the amount of inter-DPU communication could be relatively easily reduced if you could have some intra-chip communication, at least in some cases. And there are proposals for data movement from bank to bank for many years already.
Yeah, I'm also bothered that if you're going to do arithmetic, it's a problem. Should be a problem. So how to deal with that?
I have a lot of questions, but I'll ask you this one. Can you go back to your results?
Yes.
Slide, whatever, 63 roughly.
Okay. Let's see. 63. around here.
So I noticed that you're getting in some cases of this GPU, for example, 200, 300x the CPU, where you have about 30 times the memory bandwidth of this particular GPU CPU comparison. I would have to take issue, by the way, with the choice of CPU, but that's not my question regardless. You have a 30x memory bandwidth advantage for the GPU and maybe 120x advantage for the DPUs at best. But you're getting, 1,000 times speed up. In some cases, for the GPU and 300 for the GPU. Like, what gives?
So which one in particular? So you're talking about the comparison?
Generally, like
Yeah.
if you look at this, I don't remember what any of these are, unfortunately, right? But if you look, let's say, at Gen B, right, which is something that CPU is not terrible at. If you look at, MKL and what they can do, and there's a 30x bandwidth difference between the Titan 5 and the Xeon 1240, but there is a 300x performance difference. I would expect the performance difference to at best be the bandwidth difference.
Yeah, I guess I don't have a good answer for that right now. The implementation is not the same. And actually for GenV in particular, we are using a custom implementation, I think, for both CPU and GPU. So it's not really library.
No, it's fine. I'm just whatever it is, right? I would expect it to perform
But
pretty well.
you said that because so here is a Titan 5 is I think it's 900 gigabytes per second.
900 or 600 to 900, something like that. And the Xeon it's an old one, right? But I think it still had something like, effective. I think it had 30 effective or something like that, 40 max, something of that sort. So it's about 30x. But the differences are much larger, and it's about whatever 50x for the DPUs, but you have 100x to 1,000x speed up.
Yeah, that's indeed good point. I guess CPU implementations.
Yeah, it's fine. You don't have the answer.
So yeah, I mean, in some of the cases here, we have, let's say, custom implementations, relatively simple codes that we parallelized ourselves with, and I think GenV is one of them, with using OpenMP. And so, yeah, it might not scale very well when you increase the number of threads. So, yeah, this might be an issue with the actual implementation. I think it's the case of GenV.
I have a couple more questions, or they even require more discussion, so I'll leave them for discussion. But any other questions? Any more questions? We have plenty. Well, let's thank Juan one more time.
Thank you. Yeah, thank you very much.